Let's sketch another row so that we can get some practice doing this. We're going to look at the sketch of the graph of r is equal to 3, the sine of 2 theta. And so now that we know how this works, we're just going to focus on finding the tips of the petals and where it goes back to the pole. This one is a different rows because it's of the sine function and not the cosine function. So I will plot my r and my theta. I will always start with 0, and when I plug 0 in, I will get 0. So this means that I'm beginning at the pole itself. I can figure out where the sine is going to be 1 when I do pi over 4, because then that will give me the 3 when I plug pi over 4 into the function. If you need to pause the video to make sure that you get the same value, please feel free to do so. I'm going to go out every other notch in order to plot this. So I'll go out 3 and around pi over 4. Not up, but around. And so if I'm connecting this and we know what the rows is going to look like, it'll look something like that. And once we go to the tip of the petal, we know we have to come back. And so that's going to occur at pi over 2. And when I plug pi over 2 in, I'm going to get 0. And so at pi over 2, we're back at the pole. This is a 4-petaled row since the number inside is 2. And since it's even, that means we have 2 times 2 petals, which is going to be 4. So we have to do this again in order to get the other 4 petals, or the other 3 petals. So from pi over 2, I'm going to go to 3 pi over 4, which is going to put me at -3. So I will go out to -3. Out to -3, and then from there I go around 3 pi over 4 radians. So 3 pi over 4 radians is going to put me at 7 pi over 4. And so that's going to be right there, right? 1, 2, 1, 2. So my petal will come out to there. And then we know we're going to have to go back to the pole. Now, the only reason that you would need to keep the chart going for this is so that you are clear as to where a petal starts and where a petal ends. So for example, one petal would be encapsulated between 0 and 0. So this is one petal here. And now we've gotten another petal from this point here to this point here. And so that's one complete petal. We have 2 more petals to graph, so let's go to 5 pi over 4. Plugging in 5 pi over 4, I'm going to end up with 3. And so we can go out 3 and around 5 pi over 4 radians, which is going to put me right there. And you can almost sort of feel as you're tracing it where you're going to go, because the graph sort of pushes you in that direction. And we know we need to come back. And so if we're going to come back, we come back to at 3 pi over 2, which will put us at 0. We're then going to go from 3 pi over 2 to 7 pi over 4, which gives us -3. And so we go out -3 and around 7 pi over 4 radians. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 6 pi over 4, no, 6 pi over 4, 7 pi over 4. And this was the only place where I didn't have a pedal. We knew we had to have one here since we're doing this. And then we know we have to come back to the origin. And we come back to the origin at 2 pi. And so that is our 4-pedaled rose. Another graph that's going to be making a featured appearance in the last part of our course is something called the cardioid. And you see the word cardiac almost in there, cardio, heart. So this is supposed to have a heart shape. And of course, we can have different kinds of cardioids. It isn't important that you master the art of graphing it as much as it is that you master the art of locating points on the graph. So if I were to take a look at this particular cardioid, let's pull this down a little more. And we don't know what this looks like, so we're going to have to enter some points in. I tend to encourage you to use points that are easy to evaluate so that you don't end up with square roots. So if you end up with like a square root, then that's probably not a point you want to use. If we were to put 0 in, for example, we would end up with 2 minus 2, the cosine of 0, which is just going to be 0. And so what this means is that I'm going to be starting again at my pole. The next point after that I'm going to choose that is not going to have a square root in it is pi over 3, because the cosine of pi over 3 is a half. 2 times a half is 1. 2 minus 1 is 1. And so I go out 1, and I'm going to do what I've been doing, which is every other is going to be 1. And so I will go out 1 and around pi over 3. And just, you don't have to be precise about it. Just use a curve to sort of connect the two. Pi over 2 is the next point that I chose. So cosine of pi over 2 is 0, which means this will just be 2. So we go out 2 on the polar graph and around pi over 2. So from here, we have to sort of connect to that. The next point that I want to pick, I am going to pick 2 pi over 3, because I will end up with 3 when I put that in. And so I'll go out 3 and around 2 pi over 3, which puts me here. At pi, when I plug pi in, I'll end up with -1 for the cosine, and so I'll end up with 4. So we go out 4 and around pi. And so that's half of my heart. We can complete the heart if we go to 4 pi over 3, which we'll end up just going backwards now. So the next point is we go over 3 and around 4 pi over 3 radians, which puts us here. Not there. We can do 3 pi over 2, which will give us 2. So we go out 2 and around 3 pi over 2, which puts us here. I seem to have trouble staying on the same circle. And we have 5 pi over 3, which will give us 1. So we would go out 1 and around 5 pi over 3, which would put us there. And we can complete the unit by going to 2 pi, and we would end up with 0. And so the effect is complete, and we have what it does look like a heart. Now, one thing that's different than the heart is that this here should not be a point. It should actually be smooth. So try to make it as smooth as you possibly can make it look. The only point that we have, or cusp, is this point right here. At this point, the derivative, if we were finding derivatives, would be undefined. And so that is our cardioid. Next graph I'd like to finish off with, and this is the last graph that's going to be appearing among these graphs. So the graphs basically that are going to be necessary for you to be familiar with, not necessarily masters of graphing, but the circle, the rows, both of odd and of even petals. The cardioid is also going to make an appearance, and the last one is the limason with an inner loop. Not limacon, by the way. This is limason. The French cedilla makes it a s sound. So this is going to look a little like a cardioid, except it's going to have a loop inside of it, and we'll see that as we go to plot our points. So let's plot some points. Again, I strongly urge you, do not plot anything with a square root. Try to stay away from things that will produce square roots. You know that you're going to connect things in a curvular manner. So starting with theta being 0, if I were to plug 0 in, I notice I start out with 1. So I'm going to take the same approach. Every other notch is going to be a value. And so I'm going to start at 1, 0, which is right there. The next point I'm going to pick is pi over 6, because when I put pi over 6 in, I will end up with 0. Which means that I travel from my point here to the pole and just make it curvy. This is sketching. We're just trying to understand where points lie and how it relates to the graph. That's it. Pi over 2, when I plug it in, will give me -1. So what that means is now things get interesting, right? I have to go out to -1 and around pi over 2 radians in the counterclockwise direction, which puts us right here. And so I trace and a curve there. You don't know where you're going to end up, do you? Because the next point after that is that I'm going to pick is 5 pi over 6. It does not produce a square root. It also puts me back at the origin, so, or the pole. And so I come back to there. And so what this means is now I have created my loop. There's my one loop. Where is this function going to go next? Let's try pi. And when I put pi in, I end up with 1. So go out to 1 and around pi. Let me change my pointer color so that we can see this a little bit more clearly. So I trace now, since I'm at the origin, I'm going to trace this way. um, to get to where I want to be. Let's do 7 pi over 6 for ease. 7 pi over 6 is going to produce a positive, when I put it into 2 sine theta, will produce negative 2 times 1, or negative 2, a negative 1. So 1 minus minus 1 will be 2. So what this means is I go out 2 and around 7 pi over 6, which is going to put me there. I then chose 3 pi over 2, and I end up with 3. You, of course, are allowed to use a calculator to do these. So don't feel like you need to be, your unit circle needs to be memorized, although it should, but I'm okay with you using a calculator to calculate these. So we would go out 3 from the origin and around 3 pi over 2 from this location. Oh, I went off the circle. And we end up there. I can do 11 pi over 6. I'll let you do the calculations. It'll give you 2. So you can go out 2 and around 11 pi over 6, which would put you there. And you can see where this is heading. We're heading back to whence we started. So if we go back to 2 pi, we'll end up at 1, which is exactly where we want to go. And so we end up with what's called a limacon. Outside of the picture, it looks like this, or out of the graph. So we end up with what's called a limacon with an inner loop. So this is the limacon with inner loop. These graphs are going to be making an appearance because what we're going to be interested in figuring out is how to find the area of the regions bounded by the graphs. One thing for you to start to think about with regards to finding the area is notice that these graphs cannot be grouped or be broken up in exactly the same way, because since they're polar graphs, we're looking at more or less sectors. And so when you're looking for area, you're going to be looking at sectors, and these sectors cut through parts of the graph, and they cut through the parts of the graph in very different ways. So understanding how the system of polar coordinates is really important as we start to move into the calculus that is necessary for us to learn in Calculus 2.